Good afternoon, everyone, and a good morning and good day to everyone. So, I welcome you all on the behalf of Asian Development Bank Institute on for this workshop and the training program on impact evaluation methods. So, in this workshop, we will be going to focus on the difference in differences approach. I welcome our speaker, Dr. Oleg Badunenko from the Brunel University. He's serving as a faculty of the economics and has a specialization in applied microeconometrics. Oleg's focus is on efficiency and productivity analysis and the various areas of the societal life, wherein he used to provide and develops and applies the best practices methods. He is also a practitioner as well as the software developer. So he has a couple of packages in the Stata and R. Before I hand over the session to Dr. Oleg, so I would like to provide some house rules for the speakers and the audience. For speakers, please turn off your video and the mic all the time. When time allows the question and answers to be, we'll conduct the question and answers. Chat box is available only between the speakers and the host. For attendees, chat box and raise hand are not available for audience. Type your questions in the question and answer box at the bottom of the Zoom. So you can see the arrow sign and you can type your questions. We will address the question and answers as time allows and will request the speaker to deal with those questions. Comments are not available for the question and answer box. This event may be photographed, streamlined, or video recorded. By attending, accepting connection, or continuing participation in the event, participants thereby consent to the possible use of their name, likeness, voice, spoken or written comments, or papers, presentations in whatever the form, in all media, publications, video sharing, websites, recording, disseminations, or other external affairs purposes for the Institute without compensation or permission. All sessions will include the practical demonstrations using the relevant software, so particularly the Stata or R. Participants must have the software installed on their laptops prior to the session. ADBI will not provide the software subscriptions. So with this, I would like to welcome all the participants and as well as to our speaker and hand over the session to the speaker for to initiate the program. Thank you. Dr. Oleg, over to you.
Yeah, that's a very great introduction. Thank you very much for having me. I really appreciate it. With this in mind, and to be conscious of time because we need to cover a little bit of material, I will start without further ado. So what I will do, I will just start sharing my screen. Okay, share. And I would like to confirm that you can see the full screen of my slides.
Yes, we can see.
Okay, perfect. Right, so today, this is about 4.5 hour session, which is broken down into 3 sessions. We'll have 1 hour and 15 minutes, then we'll have a break, then 1 hour and 15 minutes today. And this will be mostly devoted to conceptual issues and issues of understanding of foundations behind difference in difference approach in impact evaluation methods. And tomorrow there will be a 2-hour session, which is completely devoted to the using the Stata software in applying the methods that I will describe and discuss today. Right now, I have provided a link to a shared folder where you can find the materials. And for now, you will only find several literature sources and these slides that I'm presenting right now. I will do annotations like this, and they will be saved in a separate PDF file, which I will also make available in case you will find it useful. So let's get started with the session. Okay, so the agenda for today's two sessions will be as follows. I will first discuss foundations and intuition behind what it is that we would like to measure. And I will try to make an example to which everybody can relate, and so that it's becoming more and more clear as we increase the complexity of applied methods. Then I will mathematically formulate what it is from mathematical point of view that we are interested in estimating given data. Once we've introduced that, we'll consider what is the most important part, or the assumptions for identification of parameters of interest that we would like to estimate. And as I will mention today in the session, the difference in difference approach is one of the methods that is currently used to evaluate policies. We will concentrate today on difference in difference approach. So I will go into detail of the canonical difference in difference approach. We'll look at how it is possible that we can estimate the treatment effect that we would like to estimate. And finally, we'll go with an estimation. And so that's probably the most interesting part for you. And if everything else before that is actually very familiar to you, I apologize in advance. However, for some of you, it would be a new material, and so it would be paramount for me to explain this to somebody who has never touched this topic, so that we know what we are talking about and everybody is on the same page. Once we've covered the canonical, the so-called 2x2 approach, where we have two time periods and two groups, we will move on to a case where we have multiple time periods. And so that's more interesting because more and more panel data are available. And so more and more interesting applications will be out there where you could apply the same principles that we are going to consider today to more complex tasks. And given that I will try to make a lot of emphasis on the foundations and what we are trying to estimate, I hope by the end of the seminar you will be equipped with the tools of understanding when new methods come out, and so you'll be easy adjustable to what's coming next. So let's get started with the foundation and intuition. And before we come to the actual material, let me just very briefly again manage your expectations with regards to what will be the topics and what will be the learning outcomes from this training. We'll cover the topics where we introduce the potential outcomes, no anticipation and identification of the methods. We'll look at various estimators of treatment effects, like inverse probability weighting, matching, doubly robust estimators. And we will cover the staggered interventions. Okay, so these are three huge topics as I can see them here. Now, by the end of this training, I hope, as I mentioned before, that we'll get this conceptual and practical foundations of the DAD approach. We'll apply the kind of theoretical potential outcome approach, but we'll see how it comes to light when we actually estimate the difference in differences approach, right? We'll look at the, you'll be able to understand the key assumptions that underline so that you are not going to make a mistake in your own application where you apply differences in differences approach. And we will consider, or you will be able to understand some similarities and differences between various methods, especially given that abundance of software allows you to obtain different estimators and you'll see differences. So you'll need to know what to expect and how these differences come about. And finally, that's what's left for tomorrow. We are going to study several data commands and show their flexibility in estimating treatment effects. Okay, before I go to the next slide, there are... Okay, so the Zoom chat just shows the link, so that's good. All right, okay, so let's move on to the very important topic, which is the potential outcomes, right? So here we need to understand what it is that we would like to measure. Now, we observe causes and effects every day in our life. And usually we would use some very not scientific way of saying things which we're trying to measure today. So for example, somebody had a headache and it went away because somebody took a medicine, right? We would never think about this as the cause and effect, right? We just know on an everyday basis that if you have a headache, then it makes sense to take medicine and then the headache is going to go away, right? We would also say, without actually contemplating what stands behind this, is that somebody wanted to get a good education, so they went to college so that they have a prospect of getting a better job, right? And again, here we are using the casual language where actually the causal analysis stands behind it. And why can we use such language and such formulations is because somebody in the past has conducted, let's call them natural experiments, where, you know, there were some exposures in the past where people were taking medicine and headache went away. So it is conducted experimentally that headache tends to go away when somebody takes a medicine. In the same way, the past could be a guide for somebody who is looking for a job, that it is worth taking a good course or training like you are doing in order to get a better position in a job. Now, the fundamental notion that we are going to consider is that causality is tied to an action. And you will see in the literature or in discussion different ways of denoting this action. So it could be a manipulation or a treatment or an intervention. And this action is applied to a unit, right? And unit could be anything. It could be school, it could be a hospital, it could be the whole city or the whole country, right? And there are various scenarios where this action is taken to a unit. Now, I will prefer to use the terminology intervention or treatment, and this literature is usually using the term treatment, so I will stick to treatment and I will use this. Now, given the unit, which is, as I said, is a school or a city or a country, and the set of actions or some interventions, we can associate or we can have a pair of action and a unit with the potential outcome, right? So for example, here in coming back to the top item here, I could say that I took a medicine, but at the time that I took a medicine, I could have followed an alternative course of not taking a medicine. And so in that case, a different outcome might have resulted. So the purpose here, and this is again, let me come back to this past exposure, is to understand a particular individual is taking medicine going to help them the headache to go away. But it is equally important to understand the meaning of the potential outcome, because what we observe is something that cannot be changed. However, I want to draw attention to this could have, or I also like to call it what if scenario. So what if somebody has chosen a different path? So what would it entail for the actual potential outcome, right? And we are saying this is potential, not observed outcome, because we do not actually observe it, but there is a potential for this outcome to exist. So we want to get to a definition in a very everyday language, what's causal effect. So let us consider a single unit, right? So let it be me, for example. And let us consider me in a particular point of time, and I have a headache, and I am thinking, do I need to take a medicine or not, right? So in this table, we have a unit, which is me, and I have two different actions that I can take. I can either take a medicine or I'm not going to take a medicine. And the potential outcomes that come out of here would be if I take a medicine, then I'm not going to have a headache. And if I do not take medicine, then I will stay with my headache. Now, the causal effect is the observation that we are making that there is improvement, right? Or, I mean, so here it's improvement, but generally we will say a change or difference or I can also say again, right? Due to medicine. So there is some change or improvement due to medicine. So that's why I'm trying to treat myself to this medicine. And that's a definition of the causal effect. Because I have taken a medicine, right? I have this improvement. Okay. And so here we would like to extend the possibilities of potential outcomes that are out there in the example of headache and the medicine. Now, in this particular example that we considered in the last slide, only two potential action units are possible, or, the unit level causal effect, the comparison of these two outcomes involves actually four possibilities, right? So here, what I've drawn is that we can take a medicine or not take, or I can take a medicine or I cannot take a medicine. But what I've considered is that if I take medicine, then I will necessarily have no headache, right? But it is equally possible, and this is what comes to this potential outcome framework, that maybe my headache is not going to go away. On the other hand, if I do not take medicine and simply by probably over time, my headache is going to go away, so I could have a different potential outcome, right? So in this table, what we've seen are just two values of unit level causal effect, right? However, let us consider this four possibilities that we have, right? So let me just erase all the unnecessary clutter. So the first outcome is very logical, right? So the headache is gone only when I'm taking medicine, right? So, however, this is where I'm going to consider two alternatives. I'm taking a medicine and I have no headache. I am not taking a medicine and I still have a headache, right? So that's a very straightforward expected outcome, which was presented on a previous slide. The second possibility is that there is no effect of medicine with a headache in both cases, right? So whether I am taking medicine here, right, or I don't take medicine here, I will still end up with a headache. Maybe because my headache was strong, or maybe this particular medicine is not effective on me. However, the result is going to be that I'm going to end up having headache whether I'm taking medicine or not, right? Now, the third outcome here is that there is no effect of medicine and headache is going to go away in both cases. Now, here, let's look at the treatment state. So what we have here in parentheses, this is, I'm calling the, oh, let me just, my computer is quite slow. So I'm just going to call it, oh, I do not need to touch. So let me just erase this. So what we see in parentheses, treatment state, right? And treatment state in the third case here, so let's consider the third case, no medicine and headache is still going to go away in both cases. So you see the treatment state, I'm taking a medicine or I don't take medicine, right? However, in both cases, the headache is gone, okay? Now, the fourth case, so let me just emphasize it here. The headache is gone only without medicine. So this is very unlikely scenario, right? However, it is still possible. And again, the possibility is that there is no effect of medicine on me, and with time, maybe some good news just made the headache go away, right? So we see here that if I'm taking medicine, I still have a headache, but if I don't take medicine, the headache is going away, right? Now, what we can take from these 2x2 scenarios here is that we can identify some zero causal effect from the medicine, right? Now, in the second case, we are saying there is no effect of medicine, so there is zero causal effect of medicine. In the third scenario here, there is again no effect of medicine because headache went away without taking a medicine, right? In other two cases, in the first and the fourth, there is the causal effect of medicine, right? So in the first case, make the medicine making the headache go away, and in the fourth case, the medicine does not allow the headache go away, right? So what we see here is that most probably in a casual language that I considered in the very first slide, people would most look at the causal effect of medicine taking into account this very first scenario. However, I want to draw our attention to a possibility that if there is a treatment, there will be necessarily 4 different potential outcomes. And this is the premise, this is the foundation that we would like to take into our estimation. Okay, so we had this one definition of causal effect. Let's expand it even more. So now we are going to compare 2 potential outcomes. Now we have 2 parts in this table. So we have this as the first part and this as the second part. So the first part is exactly as before. We have 1 unit and we have medicine, right? And we have no medicine scenario, and one does not allow, so if you do not take medicine, then we still have a headache. And if you take medicine, the medicine goes away. So our causal effect would be the improvement. And what we know in this particular case is that the actual treatment was taking a medicine. And what would be the observed outcome? Observed outcome is going to be that headache went away. Right. Now, so what can we see here is that even though the unit level causal effect may be well defined, by definition, we cannot learn from its value because it's just a single realized potential outcome. Suppose everything happened on one evening, so we have just one observation, and if it just happened, we cannot generalize it because it's just one potential outcome. So let us consider what can be what can constitute the program evaluation, and we'll come to the notion of counterfactual causality. Now, in econometric literature, and I mean, obviously, we are looking at methods, but we are looking at social sciences literature on program evaluation. It has its roots in epidemiology statistics and the so-called literature on treatment effect estimation. And because it has its roots there, I will use this terminology with the treatment because somebody is treated in order to see the effect. Now, here, the causality assumes the form of counterfactual causality. What this counterfactual causality actually means? It's a comparison of the outcome of the same individual with and without treatment. You see, so this is a very subtle but very important difference, which is also going to be used in the difference in difference approach later on, well, when we will see. So we are taking the same individual and we compare the outcomes with and without treatment. How is it possible? So if we go back to our example here, we know that in one evening, if I have an effect, if I have a headache, I can either take medicine or not take medicine, and I could look at whether it has helped me or not, right? However, what this counterfactual causality here states is that on the same evening, the same individual me will be both treated and not treated, right? And if you translate it into the language of previous slides, we are going to say, we are going to compare the outcomes where I have taken a medicine and I did not take a medicine. So this is the situation we need to get our head around. And so this is the counterfactual causalities that we are actually willing to measure, because only in this case we want to see the causal effect of taking the medicine. Now, in this concept, the treatment effect is defined as the effect of specific treatment variable excuse me, which is applied on the so-called target variable once the effect of the potential confounder is ruled out. We'll talk about confounders later on in greater detail, but for now we are just making these definitions and introductions. Now, what could this treatment variable be, you may ask? And depending on in which context you're talking about this, it could be, for example, a training program, right, for unemployed people, or monetary support for firms' investment decisions, and so on. Right now, for example, if you take these particular course that you are taking, so you hope that once you take this course, your understanding of the impact evaluation methods is going to improve, because this is your anticipation that you would like to gain more knowledge in this area, right? Whether you understand more because of taking this treatment, this training or not, is an open question. And there is actually 4 potential outcomes that will come out of this training, right? My hope is that it will be like this first case here, where you are taking this course and you'll see improvement in your understanding. But we always have to bear in mind that there will be 3 other potential outcomes. All right. Okay. So what, again, so this is for our understanding. What do we take from this counterfactual analysis? And so this is the so-called what-if scenario. Now, suppose that we have this period of time, I'm just going to call it T0, and then we have a period of time T2, and somewhere between them, right, somewhere here, there was an intervention or a treatment. And what we have in our sample, that individuals started both from the same point and the value of the performance was at the level of 1. And then one group that actually has not been treated, and this is the solid green line, ended up performing in time period T2 at the level 1.5. And if this group has been treated, right? So again, we are talking about the same individual, remember? So this is something I need to write. The same individual, right? And we are saying that if an individual has been treated and the same individual has not been treated, and the treatment is effective, this is going to be the effect of the treatment, of the intervention. And we can see that we can measure this effect, and that's going to be the 0.5 in this particular case. So this what-if scenario is nothing else than a theoretical construct where we are saying that some individual may have been treated, and we want to look at the difference between when this individual has not been treated and it has been treated. And we would like to actually measure the difference between the observed performance and the counterfactual performance. Okay, now what happens is that it's not possible to observe a single individual in both states, right? Because as I have given you the example with myself in the evening, taking a medicine and not taking a medicine, and it's difficult to see the causal effect, right? So, and the definition here of causal effect, as we have introduced it, it does not require more than one unit, right? However, it's not possible to observe those two states. So learning or, identifying the causal effect will require observations of multiple units. And the paradox here is that because the single unit can be observed at most in a single potential outcome, right? We must gather data on multiple units to make causal inferences, right? Even though we are going to deviate from this counterfactual performance that we have just introduced, we will need to consider multiple units. More precisely, we need to observe multiple units or multiple individuals, whereby some of them will be under the treatment and the others will be not treated. And so here come the terminology again from epidemiology, is that we have two groups. We have one cohort which we will call control cohort. So this is the cohort that has not been treated, and we'll have a treatment cohort. I'm going to return to this terminology, but I just wanted you to be familiar with this. Okay, so once we have multiple units, what does it mean for our empirical analysis? Now, up to this point, we have me as the first unit. So let me say this is I equals 1. Okay, and we still have the same scenario as before. I'm not going to repeat it. However, here we have a second unit that, let's assume that's you, right? And the potential outcomes that come out of taking medicine or not taking medicine would be not the same as with me, right? So if somebody is going to take a medicine, right, the headache is going to go away. And if you are not going to take medicine, your headache is still going to go away, right? Now, in this particular case, what will happen is that the causal effect, and here let me take of taking medicine, is none for you. Okay? So this is our first realization, is that not all treatments actually lead to changes and to improvement. And you can see why. Because in this particular case, you, for example, are not going to have a headache irrespective of whether you're taking a medicine or not, right? And so what would be the actual treatment here for this individual, this unit U? You're going to be in a control case because you're not taking the medicine, right? And the observed outcome will be no headache, right? So you see how this potential outcomes play out, and you can also see how we can use this in order to define our data. Okay, so now we are finished with the intuition. What kind of potential outcomes will be here that we are going to consider and translate into what we would like to estimate? And so let me talk more about the parameters of interest here. And let me briefly describe the setup, because we're getting into the realm of the data analysis here. So we have a well-defined population. And so what does it mean for us is that we have independently and identically distributed population. We do not have some non-random sampling procedure, right, which should be very important for us for identification purposes, as we know that we cannot have a consistent estimation if we have some dependence, right? And for each population unit, right, so that's really important, there are two potential outcomes. And remember here that this number in parentheses tells us about the state in which the observation or population unit is. And so this observation is in the control state. So this is without treatment. So again, I want you to get used to this terminology where I'm saying control or treated group. So control is without treatment. So we're just letting this observation to go on as they were, right? And the treated group, so this is where state here in parentheses is denoted by 1. And so this is the treated state. Now, what is this treatment? The treatment is caused by the treatment variable, and this is the binary indicator here, D. And D equals 1 denotes the state of treatment or an intervention, right? Again, I'm trying to use several notions here, but for us, it's always treatment. Now, let me take a word of caution here is that this this binary, right, is I will just say it is equal 1 if treated and 0 control, right? However, there are further methods which are beyond this training, is that the treatment is actually continuous. Right? And it will be on the interval from 0 to 1. It means that somebody could be treated only halfway or 75% or 60%. Now, as I mentioned, this is beyond this training because it requires different treatment econometrically. However, here we are going just to very roughly, very rapidly separate those who were treated and those who were in control. Whereas, as I said, in the modern methods, it is possible to have a continuous treatment. And so continuous, not in a sense that it continues over time, but that it is people are treated in different fractions. Okay. But for now, for this particular training, we're going to assume that D takes values 0 and 1. Okay, and so here again to terminology, and this is what we have seen in a table about the causal effect, is that we are trying to get the gain or, the difference or, improvement, right? So we could tell it in a different way. And the gain from treatment, right? And so that's really important, is that we want to compare the performance. So this is the actual observed performance, and this is the counterfactual one, right? What if somebody has been treated? We want to look at the gain of that particular treatment, right? If we add subscript I, we are going to look at the gain for a particular individual. So we have this yi of 1, yi of 0. And what we can state is that when we go to an individual level, the gain could be positive for some individuals, and the gain could be negative for other individuals, right? So in this particular case, if we come back again to our table. So you see, all we considered here wasn't in vain. So let me go to 4 potential outcomes here, right? And what we mentioned here is that in 1 and in 4, we have non-zero causal effect of taking medicine. And for individual 1, the causal effect is positive, or the gain is positive, because somebody has taken a medicine and the headache went away. However, in case 4, the headache gone without medicine, right? So it's in a way you're not taking a medicine and the headache goes away, right? So that's the negative gain that is obtained from taking the meds. Okay. And finally, introducing the effects that we are trying to measure, or that econometricians are measuring in social sciences and economic sciences, are the following. Now, this average treatment effect, which is also known as ATE, is the gain in the population. So this E, or expected value, means that we are going to look at the average across the whole population. So we're just going to look at both treated and control group, right? Or in treated and control state. And that may be of interest. However, in most cases, what economists and scientists in social sciences will be interested in is the average treatment effect on the treated, right? Because we only want to see whether those who were taking medicine have obtained effect and the headache went away. And you see how this tau ATT changes in definition is that we are only looking at individuals here where the treatment variable is equal to 1, implying that we are only looking at individuals that were treated. Okay? And so that's the most interesting part, because, as I mentioned, you really want to look at the effect of the treatment, right? And you want to look whether in this subsample the treatment has led to some gain, right? And the final definition, for the sake of introducing it, we may want to look, because we're in a potential outcome framework, we can look at the average gain for those who actually were not treated. Sorry about this. Not treated, right? So we have the subpopulation where D is equal to 0. And so this tau is called ATU. So this is the average effect on the untreated. Now, all these 3 effects, they are interconnected, and it is possible to show that the overall treatment effect, or tau ATE, would be a weighted average of the ATT and ATU. So average treatment effect. So this is probably the most important one that we want to look at. And it is weighted by the probability of being treated, right? So this small p here, small p, is nothing else than the proportion of those who were treated. So for a binary variable, that's how we can estimate this probability. And needless to say that this probability lies between 0 and 1, so we are not going to end up having negative weights, right? Now, if we have heterogeneous treatment effects, meaning that these effects are different for different individuals, then the overall treatment effect and the treatment effect on the treatment can be very different. And needless to say, in order to estimate these effects, we need to make assumptions. And which assumptions we're making actually matter for estimation, as we will see later on. Now, as I've mentioned, this particular training concentrates on the treatment effect on the treated, because this is what the mostly scientists are interested in, right? So you may want to look at the different type of literature if you're actually interested in estimating the overall treatment effect, but I will be concentrating here on the most common measure of the treatment literature. Okay, so let's consider the sampling, and we're still in the section where we're trying to identify what is the parameters of interest we're trying to estimate. Now, we assume independent, identically distributed observations that come from the underlying population. And just again, looking at what we can do, if we had the observations as we wanted them to have at the very beginning, where we introduced the definition, right? So let me just look at this definition of counterfactual causality that we considered here, right? So the second item here on the slide. So causality assumes a form of counterfactual causality. So we compare the outcomes of the same individual, right? So this is the paramount here in this definition. The same individual appears in the treatment state and in the control state, right? And so this is exactly what we have here. So let me just move on to the template, right? So we do not have the need to assign units to control a treatment if we have the observation of this individual in both control state and the treatment state, right? So if we have such data, then it is very easy to calculate the average treatment effect in the whole population, whereby we're just going to take the mean value of the difference between these observations, right? The problem here is that for each individual eye, as we mentioned before, we can observe an individual only in one state, either in a treatment state or in control state, right? So there is no other possibilities to observe this individual, right? And what we observe actually in our data is the YI and DI, right? So we observe the individual's performance, and we know whether this individual has been treated or not. So the outcome variable here, let me spell it out for ourselves. So YI would be 1 plus 1 minus DI multiplied by individual I in a state control plus DI times performance of an individual in the treated state. So let us recall for our particular problem here is that treatment effect for individual I is equal to, that's our definition here. Okay, so this written in blue is nothing that we didn't know before. So what we can from here get is that y I in the treated state is equal to individual I's performance in control state plus treatment effect, right? So we just put the this term on the left-hand side and we have the equation. Okay, so now we can come back to the problem and open the parentheses, and we'll end up having y I 0 minus d y I 0 And let me just open the second parenthesis. So that's going to be plus ti yi0 plus di times treatment effect of I. Okay, so these terms here will cancel each other out, and we'll end up having yi in the control state plus di times treatment effect. So here you can see that we can represent our outcome of the variable yi as the outcome of an individual in the control state plus probability of being treated multiplied by the actual treatment effect. Now, in order to, before we come to the final assumptions here, which are important for estimation, we want to make one very important conceptual assumption, and that's the Sutva assumption, as it came to be known in the literature, right? And so what this assumption actually comes down to is that we exclude the possibility that treatment of one unit actually affects the outcome of another unit, right? So we do not want a situation where so for example, if you take a training and or even if individual takes a training in order to find job, we do not want to have the assignment of a treatment in such a way that decision of one unit actually influences the outcome of another unit, right? So the potential outcome for any unit do not vary with the treatment assignment to other units, right? So that's really important that we don't have this spillover effect. Excuse me. We don't have a spillover effect on the potential outcomes of different individuals here. Very succinctly written, we do not have interference in our assignment and potential outcome, and there are no hidden variations in the treatments, right? So if this assumption does not hold, then the potential outcome of individual I actually depends on the treatment of individual 1, of treatment of individual, I don't know, 2, and treatment of individual n, right? We do not want to have that. And econometrically, the best we can do here is we can, for example, look at the treatment of students, but then take into account the class in which the student studies or the school in which the student studies, right? Or just look at the clusters. So this is the best we can do in order to try to alleviate the violation of the stable unit treatment value assumption, right? Irrespective, I just wanted to let us know that we will assume the validity of this assumption throughout the whole train. Okay, so let's have a look at the assumptions that are required for identification of the average treatment effect on the treated that we have introduced before. So now, as I mentioned before, all we want to do is we want to estimate the average treatment effect on the treated. And so this is the definition that we've introduced before, right? So there's a difference between the outcomes in the treated and control state for subpopulation of those who were treated. And because the expectations are linear, we can split this expectation into the difference of expectations here. And it is very easy to see that the first expectation, which I box now in red here, it's readily available because the variable for the whole population, random variable y, if you multiply it by the treatment variable d, it's very easy to see. So this is our y, which is spelled out. And so d squared y1, sorry, so that should be 1. I should correct this, right? And that should be 1. Okay, so that's sorry about this mistake. I will correct it in the slides and put them on the shared folder. Now, so d squared is actually equal to d because this is just 1 or 2, right? So if you square it, nothing changes. However, here d is equal to 1, so this term, whole term is equal to 0, right? So that's very easy to see. And moreover, I'm not going to go into detail here, but so this term here, right, which we want to estimate, the sample average here of the potential outcomes of individuals in the treated state in probability will approach the term that we are actually requiring to get for average treatment effect on the treated, right? So basically, when we get this term here, we can plug it into this box term, and this is the one that we can estimate relatively easy, right? However, the problematic here would be the second term, right? So this is what I call the hard part. So we need to make some assumptions in order to estimate this second part, because we do not actually observe that part of the expectation, right? Because see, so this is the potential outcome of individuals who are in control state among the subpopulation of those who were treated, right? So we do not directly observe that. And in order to estimate this expectation, so if anything, if you want to explain the difficulty behind the treatment literature, so this is encapsulated in here. So there are different ways to estimate this expectations, and that's where we are going to get different estimators of treatment effects, right? It's how this term is actually estimated. And we will see later on when we come to this estimation part, how this term is estimated is actually defining what kind of treatment effect is coming out, right? Okay, so how can we get this term? The probably the strongest assumption that we can make and the easiest way to estimate would be to assume that the potential y is the same for both treated and control group. Okay, so this is the assumption we can make, right? Just to speculate where we're going to end up. And once we assume this, we rule out the possibility that an individual eye is assigned into a treatment or self-selects themselves into a treatment based on the outcome of the untreated state, right? So they know that this is what is going to be their outcome in the untreated state y0, and based on this outcome they are self-selecting, or somebody is selecting them into this outcome, right? In other words, we can write this that expectation of the outcome in the untreated state y0 does not depend on the assignment of the treatment, right? So assignment is independent of the untreated state in of the outcome in the untreated state. Okay, right. So this is a very strong assumption, and you know, for example, that somebody who would be willing to take a training when they are unemployed, because they know that if they do not take this training, then obviously they're not going to have enough knowledge to find job, right? So already in this particular case, this assumption is violated, right? So this assumption is very strong. However, what's allowed within this assumption is the correlation with the gain, right? So if somebody who is expecting that there will be additional knowledge that they are going to get from that training or from participating in an intervention, then this is allowed within this assumption, right? So, for example, somebody's going to be assigned into the intervention expecting a positive gain, right? So that's not going to be a problem, and then we can easily get a consistent estimate of this hard part of the average treatment effect. Now, needless to say is that we are going to say that depending on whether individual is in the treatment subsample or control subsample, the expectation of the untreated state is going to be the same, right? And if this assumption is true, it's possible to show that the averaging the potential outcomes of those who were not treated is actually approximating well the second part that we need to plug in here, an average treatment effect. Okay, so if we were able to find this, then the consistent estimator for average treatment effect that we are looking for would simply be the difference in means, right? So we're taking the potential outcome for those who were in treatment. We take the average of potential outcomes of those who were not in treatment, who were in the control group. We take the difference of those means, and that's going to be consistent estimator for average treatment effect, right? Now, what we want to know is what will happen if this assumption does not hold. Now, it is relatively easy to show that the probability limit of the estimator average treatment effect will be equal to the measures that we actually would like to find, and the term which is the difference between the potential outcome between the treated population and control population. And this term, which let me just box it here in red, is come to known in the literature as the selection bias, right? And obviously, because we do not know neither sign or magnitude of this bias, it will be really difficult to say what we have estimated when we looked at the simple average, which is shown in equation 3.13, right? And now, in order to slightly weaken the assumption that we have just made here, we are going to introduce another set of assumptions. Remember that this section is called assumptions which are needed to identify the average treatment effect. And so here we are going to consider the first fundamental assumption, and that's unconfoundedness, right? Unconfoundedness, right? So that's a complicated word, but this is the one we are going to use. Now, in our sample, we will necessarily have covariates, and we'll denote them to be capital X, bold. So what we are going to say in our assumption is that these set of covariates should be determined prior to the actual treatment, okay? And so the treatment assignment will be independent of y0. So this part here is as before that we used a couple of slides back. But now we are going to add the part that it is conditional on our covariates. In very plain language, it will mean that assignment is allowed to depend on x's, right? And within subpopulation, where x is equal to particular observation x, I could call it, x0 here. The assignment is independent of the state in the control group, untreated state, right? Control. Now, what does it mean? So you may ask, what is this conditional on X, right? And suppose here that we have the whole population. I will just have it as a rectangular, and we have different values. So here that could be x1, that could be x2, and so for x 35, right, and xn. So we're just going to have different values for x's. Now, and I will have, let me just take, within this rectangular, right? So this is what I'm calling conditional on x. Within this particular x, the D, right, the assignment in the treatment is independent of the potential outcome in the control state. Now, in this particular triangle here, once we isolate this particular x that we have, isolated here, the treatment is going to be independent, right? So in each of them, the treatment is going to be independent of y0, right? So this is what conditional on means. They may be different within any of all of this, within this pink one, right, and within this green one. So the assignments may be different between these subpopulations of axes, right? However, within a same small rectangular here, the D is independent of y0, right? And now you can see how this unconfoundedness assumption is weaker than the previous one that we have made here, where we said that y is the same for, unconditional, right? So here it does not depend on x. So here we're actually saying that the D is independent of y0 for the whole population. Now, this is a very strong assumption, as we mentioned before. So we want to weaken it, and we say D is independent of y0 conditional on x, right? And so this is our first fundamental assumption, right? Very formally, we can say that this is the unconfoundedness in conditional mean, and for the potential outcome here in an untreated state, the expectation of y, conditional here, as you can see, let me just take the yellow one. This is the treatment that is going to go away, right? So conditional on x, the y0 and D are going to be independent, right? Yeah, so that's actually what's said here, conditional on x. And so here, again, the probability of assignment does not depend on what we think the potential outcome is going to be in the untreated state. Okay, so this equation 3.16 here is saying exactly what we said before, right? So here, here we said that possibility that I is assigned or self-selects in the treatment based on the outcome in the untreated state, right? So here we're just making this very strong assumption, and we're saying this for the whole population. But in unconfoundedness assumption, we are saying that this is only conditional on x, right? So in the literature, if you see somebody saying ignorability assumption of D, so that's exactly the unconfoundedness assumption, right? So that's ignorability of D conditional on X. And so we can move on to the next assumption. Before that, obviously what I should have said here is that suppose that we have the randomized control trials meaning that we have a group of individuals or school, and we just flip a coin and we say, okay, so this one is going to be treated, and then we flip coin once more and we say this is not going to be treated. So in this particular case, we see that the treatment is completely exogenous, right? So it's not bound by any access, right? So we do not even need to consider that. Then obviously in that particular case, this assumption is absolutely fine, and what we have seen in randomized controlled trials that the average treatment effect is actually estimated using the equation 3.13, and that's absolutely fine, right? So again, we need to see the context behind which we are estimating this, and in some cases, this assumption that we have made here on the previous slide is not strong. It's absolutely fine because the treatment is completely random, okay? But in observational data that we typically have, this assumption is very strong, and so we need to replace it with a much weaker assumption, which is unconfoundedness. Okay, so what I see here is that before we move to the next session, let us make a 15-minute break. So let's continue with the training. And where we stopped here is we introduced the first fundamental assumption for identification, and that's the unconfoundedness in conditional mean. To introduce the second fundamental assumption, we first need to introduce the propensity score. I'm sure you've heard this notion before, and I'm just going to repeat it for the sake of full clarity. Now, the propensity score is the probability of treatment, and this is presented as the function of controls. So it's just shortly written as small p of x, and this is the probability of being treated given the controls, right? And so here x0 is in support of all x's, right? Now, in a more plain language, the propensity score is defined as the probability to get treated given the knowledge of x. Right. Now, here we are talking about the observational data, and here we are saying that given some covariates, there is a certain probability that the individual or the unit is going to be treated. In randomized controlled trials, we know that propensity score is just 50-50, right? So somebody is going to be either treated or not. So this is the propensity score. And now, given the knowledge of propensity score, we are introducing the second fundamental assumption, and that's the overlap. Okay, so what does it actually mean? Well, first of all, let's introduce a formal definition of overlap. The overlap assumption states that for each unit I, it must be true that the propensity score is between 0 and 1. That means that if unity is characterized by a set of attributes x that belong to both treated and control group, we can observe the probability in these bounds, right? Now, in a more plain language, it will mean that all units have a chance to be treated, okay? So what does it mean? It means that we are going to observe individuals who are treated and those who are not, but the probability that are treated may also have been not treated, and at the same time, the units that were not treated have a positive probability of have been treated, right? So for instance here, if for a particular x0, the propensity score is equal to 0, it means that there are no units in the treated group that have this specific value of x. And it means that average treatment effects, they simply cannot be calculated or identified. Now, you see how important this assumption is, in a sense that we need the comparison points in order to identify the average treatment effects. Okay. You can also, kind of think about this assumption as no one is left behind. Okay. Now, let us have a look at a very simple example in practical terms. I'm going to repeat it next day to you, but here, typical way to estimate the propensity score would be a binary choice model like Logit, and we have our treatment variable, which is equal to 1 or 0, and that's going to be trit. And we'll regress it on a bunch of regressors here. And then we are going to look the predicted probabilities, and this pH is necessarily, the variable pH is necessarily smaller than 1 and larger than 0, because this is how the logit function works. So that's exponent of x beta divided by 1 plus exponent of x beta, right? So it's necessarily between 0 and 1. And so let me just look at the statistics for 10th percentile, 25th, 75th, and 90th percentile, right, by the treatment variable. So for those who were not treated, we see that this propensity score is equal to 1 only starting from the 70th percentile, right? So only 1.15% are there, right? Whereas when we look at those who were treated, most of them were treated, right? And that starts 10% at 10th percentile. So that's pretty much stable. Now, if you look at the density, or the smooth histograms here, and we'll look at the sample that we have here for a treated group with the vertical mean vertical line representing the mean, and so that's exactly 0.5. And for a control group here, the red one, we see that the mean is very low. And that's not what needs to happen, right? Because it means that the probability for some individuals or for some axes that somebody who is in control group doesn't have a chance to even be treated. So quite a lot of empirical scientists see this as a problem, because we are not given the equal share of those who can actually be treated, right? So what's usually been done in empirical literature, and again, I'm going to show this tomorrow, is we can flag those observations where the predicted probability H is smaller than 0.1 or larger than 0.9, right? So this is 0.1, and here is 0.9. And so now if you look at the density of probability of being treated in two different subpopulations, we see that we are going to consider those observations that have somewhat equal probability of being treated. So we are matching the subpopulations in such a way that it mimics our assumptions of overlap, right? So remember that our assumption for identification here is that we need to have each and every x that exists here, that propensity score is not equal to 0 or is not equal to 1, right? We need somewhere in between, right? So we want to exclude this case, and we want also to exclude a case where propensity score is equal to 1, because it's going to be clear that this individual is, or this unit is being treated, right? So the typical practice would be to estimate the propensity score on all possible covariates, and then exclude those that go, below this or is larger than 0.9, right? And so that's a good practice which you may adopt also in your particular application. Okay, and so this is the overlap assumption that's very easily verifiable, and we'll see some influence on this in terms of which sample we are considering, how much sample is going to be reduced first, and second, what effect it's going to have on the estimation. All right, so now that we have, you see, we've introduced the foundations. We know what is potential outcomes. What is the setup that we are looking at? We know what we want to estimate here, right? We have considered the two fundamental assumptions that we require to identify the effect that we want to do. Now we want to return to econometrics and look at the differences in difference approach, right? And we will start off with introducing the individual fixed effects regression, because that's the most easy to understand and look at. Now, again, I'm not going to go into a very rough algebra, but I will try to keep it more or to issues that you can relate to. And a very old question that economists posed was, does belonging to union membership actually improves bargaining power and increases wages of workers, right? More specifically, do workers whose wages are set by collective bargaining rather than individual bargaining could be larger than those who are not subject to collective bargaining, right? And in order to look at this question from a causal effect, in this particular case of wages being set by collective bargaining, right? So here we want to understand the intervention or treatment, right? So here the treatment is union membership, right? Okay, so here we want to straight away set up it in familiar terms. It's like taking a medicine for getting rid of headache, right? So here our outcome variable is the wage, and our treatment variable is union membership, right? So let our y variable be earnings of worker I at time period t, and our dit variable be a union status in a particular time period, right? So you see we have identified or translated the economic problem into econometric problem. And given our previous discussion about the confoundedness assumption, what we want to say is that the expected value of the control outcome, which is conditioned on our axis, and our axis now consists of unobserved fixed confounders, our time-varying covariates, and time, but it does not depend, let me just emphasize it in yellow, it does not depend on the assignment. So the assignment D and the potential outcome in a control state are independent, given that we have controlled for time-varying covariates and unobserved fixed confounders, right? So that's nothing else than confoundedness assumption. Okay, so suppose that we are going to assume a linear model for simplicity. Obviously, you can do a non-parametric estimation in this particular case, but we are going to assume a linear model. And so this expected value here is going to depend on a constant term alpha. We have the time effect, we have individual effects or fixed effects, and we have our regressors here. Now, what we further are going to assume is that the causal effect of union membership, right? Remember, this is our D variable, is additive and constant. That's really important, right? Because we do not want to have a factor. We do not know how to estimate this in econometrics. And here we are going to say constant because here we are not, right? So we are not going to look at the heterogeneous effect for now, okay? So right now we are going to assume that they are constant. And so this is this small d or delta, as you will see it in the literature. And you see that it does not have an I index, right? So if we have heterogeneous, we would have di, but we have simply d, it's constant, right? For simplicity. Obviously, different treatment could be made, but we want to start relatively easy. Now, if we put together these two equations, 4.20 and 4.21, we are going to say that the whole population that we observe here would be our linear relationship that we have assumed in equation 4.20 plus the causal effect, which is our D variable, multiplied by dummy variable, right? And so here, if we are to estimate this equation 4.22 and look at the coefficient at the dummy variable, we are going to get the causal effect of interest. This is our fixed effect model, okay? However, this fixed effects model, it requires that we have a proper panel data, meaning that we have repeated observations observed in 2 time periods. And we are going to look at this example in our status session tomorrow, right? So we are going to look at this, but for now, we don't have this, right? So we're just going to consider different possibilities here. And more specifically, often the regressor of interest varies only at the more aggregate or group level, such as the city or state or cohort, right? So we don't have very proper panel data. So here I'm going to consider one example where we have an introduction of minimum wage in one of the states. And so let me just have a look. Oh, we have 1 more hour, so that's good. That's good because we have a lot of material to cover. Right. So suppose that there is a new legislation that a minimum wage has been introduced in a particular state, right? So this is what I said, that this intervention could have happened not at an individual level, but it could have happened at a more aggregate level. And that's what usually is happening, that there is some legislation which is introduced at a city level or province level in a country, but we want to see what effect did it have on firms, right? And the intervention has not targeted firms directly, it targeted an area. So, for example, suppose that the intervention happened in the city of Tokyo, but it did not happen in the city of Osaka, right? And we want to see how the firms that operate in Tokyo were affected by this. Okay, so this is exactly the example here. So in state A, the minimum wage in restaurants has been introduced, whereas in state B, there is no such intervention. Okay, and we have data on restaurants, right, or individuals where the wage has been introduced in 2 time periods. Time period 1, before intervention, and after intervention, which is time period 2. So we have 2 periods, we have 2 states, and we have a bunch of individuals in those states, right? So what we're interested to know in this particular case, and you can relate to your own empirical application, is whether employment has changed following this intervention. Okay, so that's a very practical question that we would like to answer, and this is exactly the case for the differences in difference approach, right? We cannot estimate it using a fixed effects model that we have introduced on our previous slide, right? Because we have only two indices here, and the intervention happens not at an individual level, right? So here it was an individual level, whereas in most cases the intervention happens at the more aggregate level, right? So this is what we say more aggregate or a group level. Okay. So what we can do is we can estimate the difference in difference. We can apply the logic of difference in difference, right? So we cannot apply the fixed effects directly, but we can use the logic of fixed effects estimation using the aggregate data. Sorry, this is effects. Fixed effects estimation using the aggregate data. So what we can see here is that we have a restaurant I, we have three indices here, in a state S at a time t. If there is a minimum wage, we are going to denote this with y1. And if there is a low state minimum wage, then this is the control state, right? And we can only observe one of two potential outcomes, right? So we have this missing data problem as we discussed before, right? We cannot observe a restaurant which adheres and is against the law that has been introduced, right? So the main idea behind the differences in differences setup is that we have the additive structure for potential outcomes in the control state, right? So this is our control state. And so we have here the effect for the state and effect of the time, lambda t and gamma s, which are in equation 423. So we are going to introduce a dummy variable and pay attention to the indices here. We do not have it at the restaurant level, right? We have it at the state level. So our dummy variable for high minimum wage is our D subscript S and T. And so here what we are going to assume is that the difference between the potential outcome in the treated state and the control state is constant, right? So again, we don't have the heterogeneous effect, and it's just a simple D as before. So we can set up the equation 4.22, which uses the spirit of the fixed effects. Except for now, we have three indices, I, S, T. I stands, remember, for the restaurant, S for the state, and T for time period. So our variable is also the IST. However, we have state effect and we have the time effect here. And now a dummy variable is at the level of state and time, right? So from here, let us consider the control state. And we remember that in state B, the minimum wage has not been introduced, right? So they could still, charge whatever wages they can, right? And we look at the difference between after intervention and before intervention. So if we do the algebra on equation 4.24, we will find that this difference in expected values is going to be given by lambda 2 minus lambda 1, right? So because this is just these time periods. Okay, so we're just going to see what was the change. It may be 0, right? We don't know. We just want to see that there is no change in the age over time, or rather, we would like to take that into account. Okay. And now we are going to look at the treated state, and we remember that this is the treated state here, A and A. And we are again going to look at the difference between the post-treatment state and pre-treatment state, right? And so if we write out the expectations for equation 4.24, we're going again to look at the difference between these two plus the d that we have assumed here. Why? Because simply, let me just use different color here. This is just pertaining to this capital D dummy variable. It is pertaining to the treated state A. Okay. Okay, so now that we have the first difference, right? So let me just write difference number 1, and this is difference number 2. So we have a difference for a control state. We have a difference for a treated state. So what would be in the spirit of the difference and difference estimator? We are going to look at the differences in differences, right? And so here, this is our treated difference. So this is difference number 2, and this is difference number 1. Okay, so and this is equal to this coefficient d in which we are actually interested, and that's going to be the effect of introducing the minimum wage. Okay, now it becomes clear why the approach is called differences in differences, because we cannot observe a restaurant which both included a minimum wage over 2 time periods policy and did not include it. So we need to calculate these differences in differences in order to estimate the treatment effect of introduction of minimum wage, right? And here it becomes clear why we have differences in differences. Okay, so we have the population differences in difference and how we can apply it. And this is what we are going to do tomorrow in our status session, is we are going to apply the so-called DID regression, right? In a very simple state, using the fixed effect estimation and also more complicated approaches, which we are going to consider here in this estimation session, right? So as with the fixed effects model, we can use the regression to estimate this equation. And why we are going to do this is because we also want to get the standard error for our estimate of the treatment effect. So first, we need to define 2 dummy variables. The first dummy variable is going to be treated, and it is equal to 1 if the state is treated, which is A. And we are also going to introduce a dummy variable, which we call post, and that's going to be equal to 1 in the post-treatment period, right? So that's becoming important because right now we are approaching the terminology which we're going to use later on. We have treated variable and we have the post variable. And now we can rewrite the difference in differences regression as equation 4.30, whereby we have a gamma coefficient multiplied by the treated dummy variable. And let me take a different color. We have the lambda coefficient, which is multiplied by post variable. And we also have the interaction between the treated and the post. And the coefficient in which we're interested in is this coefficient D. Okay. So this equation 4.30 is an equivalent of what we've seen before, except for here in our fixed effect estimation, this DST is equal to 1 when, right, dummy variable for, so this is DST is going to be equal to 1 if state is equal to A and time is equal to 2 and 0 otherwise, right? So this DST has its own definition, right? And in order to not introduce this particular dummy variable, we can use two dummy variables, which we define here in equations 4.28 and 4.29. And in order to see why we are going to approach the same differences and differences as before, is let us have a look at this four groups that we define on the next slide. What would be the expected value when variable treated is equal to 0 and post is equal to 0, right? If we plug them both into equation 4.30, we are going to end up with just coefficient alpha, right? So the treated is going to be equal to 0, this one, right? Post is going to be equal to 0, this is 0, and this is 0, right? So we're just going to end up with alpha. Okay, so let's consider the second case here. So here treated is equal to 0, so it's the state B, right? In post-treatment period. So we're still going to have alpha, right? So there is no doubt about this. But here what we are going to end up having is that this is not going to be equal to 0, right? So we are going to add lambda here. Now treated is equal to 0, so this is 0 and this whole thing is 0, right? So we're just going to have lambda here. Let me just, right? Okay. So next, we are going to consider, let me erase this here to avoid clutter. So here we have the treated, which is state A, in pre-treatment period. So this one is going to be non-zero. So we're going to have alpha plus gamma. And we are going to have post. So this is 0 and this is 0, right? So nothing else after that. So this is the effect we are going to have for the group number 3. And finally, for the last group here, where treated is equal to 1 and post is equal to 1. So we are going to consider this, 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 right? And so our whole effect is going to be alpha plus gamma plus lambda plus D, okay? And so again, we can write our difference in difference. So this is difference number 2, which is going to be, let me just write not difference number 2, but difference for treated, right? So that's going to be, so this is treated. So if you subtract one from another, that's going to be just lambda plus D, right? And difference for control, there's going to be this difference, right? So that's just going to be lambda. So again, if you take difference and difference, that's going to be lambda plus delta minus lambda. And that's going to be equal to delta, right? So you see that this is a more intuitive way, right? So I'm going to give you an intuition here why we consider difference in differences estimator by looking at the coefficient D here in equation 4.30, right? Because we are looking for difference in differences between the treated and control outcomes, all right? So hopefully it makes more understanding for what method has to offer here. Okay, so suppose now we consider 2 time periods, but many times often we have a situation where we have more than 2 time periods, right? So we can still use the difference in differences regression for testing the causality in the spirit of grandeur, for example. And suppose that this variable dst that we have considered in the previous slide changes in different time in different states, right? So we have more states than just two, and we have the policy that is introduced in different states, okay? So we want to know the effect of introduction of those changes, but we have more than two time period, right? So here in this particular case, we can invoke grand jury causality testing procedures to check if conditional on a state in which intervention has happened and the year effect, we can see whether the past interventions predict the potential outcome, but future intervention do not predict the previous ones, right? So we want to see that actually the performance does not introduce the intervention, right? So what we want to check is whether the intervention here causes the outcome, but not vice versa, right? So how can we do this? So one way of doing this is to introduce the future and past dummy variables and see if they are significant in the equation like shown here in equation 4.31. So here we still have our state effect and the time effect, but we also have our lags of policy, and more specifically M of them, capital M. So this dummy variable here is nothing else than the policy introduced in a previous time period, in two time periods before, up to M time periods before, right? And we will denote this D minus 1 up to D minus M as post-treatment effects measured by M lags. So we want to see whether introduction of policy 2 periods before had an effect on the outcome this year, for example. In the same way, we want to see whether the future introductions, let me just take a different color here, for example, the blue one. And so in this summation, we have the leads of the policies, right? And we have Q of them. So we want to see whether the outcome in this year is actually influenced by future interventions, right? They should not, right? Because this is our hypothesis here that intervention causes performance, but not performance causes the intervention, right? And we can run this regression and see if the coefficients D pluses are not statistically significant and the minuses are statistically significant. Exactly this has been done by Author in 2003, and that's one of the top economic journals here. So the economic question they had in mind to check is the following. In US labor law, employment is very fragile in a sense that workers can be laid off quickly for just or unjust reason, right? So just because if they are not needed, they are fired and that's it. And now in some states, right? So this is where things or intervention. In some states, courts have allowed a number of exceptions, right? Meaning that it's not so easy to lay off workers, right? And that could lead to lawsuits for unjust dismissals. So what it means now is that there is an intervention allowing for exceptions which could potentially lead to court cases. And so what it means is that firms would be, less easy employing full-time workers and more easily employing temporary workers, right? just to replace the possibility that somebody could sue them for unjust firing. Now, the main issue here is that there's some states and these some exceptions, they were introduced in different time periods. In one state, they were introduced this year. In another state, they were introduced next year, and so forth. So we do not have a single introduction time of the policy, right? And it makes it difficult to apply the methods or estimation approaches we have considered before, right? However, we can now estimate the equation like shown here in equation 4.31, where we can include both lags and leads of policy, right? Okay, so I'm just going to cut this to a single graph from that particular paper. So I'm just taking it with the full citation of that graph. And you can see the paper in the literature folder in the shared folder. So what they have found, so in this graph, this is the year of adoption. And you see the beauty of this approach that we looked at, the grand jury causality testing procedure, it does not look at separate states. It looks at all states all together. It just says in this state we have 2 years prior to intervention, and in other state 2 years prior intervention is going to be in different time period. So you see, in total, this research has been conducted for over 20 years, for almost 20 years, and that's you see very spread in time, because these exceptions were introduced in different time periods in different states. So what does estimation tells us? Well, first of all, this axis here, y-axis, shows the employment of temporary workers. Okay, so remember the setup, which is very important, is that the full-time workers could have been laid off quickly, right? But temporary workers, firms don't have to fire them. If their contract is ended, it's just not prolonged and they're no longer employed, right? So what authors wanted to see whether there was an increase in employing temporary workers in those states where there was an intervention. So what they found is that 2 years, so here let me denote this by this green, 2 years before introduction of exceptions by courts, there was no change in employing temporary workers. Once the policies have been introduced, we see that 2 years after adoption, there is a sharp increase in the amount of temporary workers being employed, right? And this does not die out, right? It just flattens out, right? So what this flatten out means is that it is much stronger than zero, and it remains there. So it means that the firms actually started to hire more and more temporary workers than they have been employing before the intervention. Okay, now look, I just wanted to give you a heads up before the estimation and multiple time periods consideration, because this is the easiest way to estimate the model using the spirit of differences and differences, using a grand jury causality type of testing. And you see how powerful that is. So it shows you the possibility to look at the intervention at different time frames within the adoption of some policy. And it allows you to show the effect that this policy had when it has been introduced in different time periods. Okay, so I think that now we've considered enough for we've considered enough of approaches before we can get to more complicated modern approaches in differences, which we will then later on consider in stator exercise. And these are the main goal is to look at the doubly robust estimators. And for this, we need to consider at least two estimators that I'm going to introduce here, right? Okay, so first of all, recall the main aim of our estimation is that we want to have this average treatment effect on the treated group. And that's a difference of two expectations. As we shown, the first term can be estimated consistently irrespective of any assumptions, right? So this is given by the average of outcomes for the treated subpopulation. But in order to estimate the second term, we need to make additional assumptions, right? And we remember that if we have a very strong assumption, which can be true for randomized controlled trials, we can just get an estimated using the average for the control state control subpopulation. But if we have a more less restrictive assumption, we can estimate it in observational data, right? So we can use the following logic in order to recover the second term in a more robust way. So first of all, so this is the term that we want to estimate, and we can use the law of iterated expectation. So I'm just going to use it, and you will see in the literature as well, law of iterated expectations. And so we can rewrite it as this expression here, right? And remember now that we can invoke the unconfoundedness assumption in order to arrive at the expression here in this equation, that expected value for observation in untreated state for treated subpopulation conditional on X is simply equal to the conditional expectation of the untreated state, right? So, okay, once we have this, we need to estimate this expectation. So we can assume some function m, it may be linear, it may be non-parametric, so that's up to us how we define it. And that's going to be a conditional mean for observation y for untreated subpopulation, right? And using the unconfoundedness, this conditional mean is just going to be the conditional mean of this function m of x for treated subpopulation. Okay, so how can we make sure that this latter condition is satisfied and can be identified? For this, we need an overlap assumption, right? So that mx can be identified, right? Okay, so as a summary of this slide, we can see that, okay, so this second term here, right? And I'm just going to introduce it here by connection. It can be identified given the unconfoundedness and overlap assumptions hold, right? So you see that the assumption that we have introduced in this section here up, they are not there just for scientific curiosity, but they are really there in order to identify the average treatment effect. Okay, so how can we get this identification to work? There are several ways in the literature how this can be identified. One of them is the propensity score weighting, right? So you would see this abbreviation as IS. Oh, sorry, not I. Propensity score weighting, right? And so first, let's note that 1 minus d times y is equal to 1 minus d in subpopulation of untreated, right? Because this is nothing else than the probability of being untreated. So when we look at the subpopulation of treated, that's equal to 0. So we can write it like that. And then we again use the law of iterated expectation, like we did here, right? And so expected value of the untreated state performance for treated subpopulation, so that's exactly our second term we want to estimate, is given by expression here, which can be simplified by getting rid of this y0, right? And so what's important here is to consider the overlap assumption. And remember what I've mentioned before is that it would be nice to have this P of x to be between 0.9 and 0.1. Why? Because if P of x is very close to 1, then 1 minus P of x is very close to 0, and the 0 goes into the numerator, and then this expectation could be exploding, right? So that's why from identification point of view, it's important that overlap assumption actually is satisfied, and we'll see tomorrow in the exercise how we can deal with that, right? Okay, so this is identification via propensity score weighting. There is another way of identifying this, and that's the regression adjustment. So remember again that we need the second term, right? So if we have our m function, which is the expected value of y conditional on control subpopulation here, right? And obviously axis, we can use the fact that for treated subpopulation, y is equal to y of 0 of untreated case, right? So that's where we're transitioning from line 1 to line 2. And then we can use the unconfoundedness assumption here to transition from line 2 to line 3 here. Okay, so what it means here is that we can have an expectation of a treated state of control state using the treated subpopulation, right? And we can use it in our estimation. Okay, so if we assume, for example, linear function for m, remember I said it could be linear, we can estimate it non-parametrically, then the average treatment effect that we're interested in, right? So we remember how we can estimate this, but this could be estimated using the imputation, right? So we can estimate it using the control subpopulation, then plug in the parameters beta from that equation and plug it back to estimate it for a treated subpopulation. Right? So this is also known as extrapolation or imputation. And that's why the whole approach is called the regression adjustment, right? Again, here, the overlap is extremely important in this particular case because we need the matching between the control and treated subpopulations. Okay. Now, in order to describe the steps, because we are going to use this also in because we are also going to use it in the multiple time periods regression. So we first estimate the equation using the control sample, right? We run a regression of y on axis, and we obtain the estimate beta. Remember that this is our linear regression here, okay? So once we have this beta, we can calculate the average for the treatment subsample, right? And plug these estimated beta in here, and that's going to be the average treatment effect using the regression adjustment type of estimation, okay? So it can also been shown that this coefficient, this tau that we have found in equation 5.35 can be retrieved as the coefficient at the dummy variable di in a regression in which covariates are centered about x bar 1 in the interaction term, right? So in this interaction term here, right? Now, you may say, why should we bother with equation 5.36 if we can also retrieve it from equation 5.35? And the issue is that if we have it as the coefficient at the variable, we can get the valid standard error, right? So we not only estimate the average treatment effect using the regression adjustment approach, but we're also going to get the standard error. And we know that standard error is very important to make statistical inference. Okay, so the other approach is inverse probability weighting, right? Is for us to also understand what the software does when we apply it tomorrow. And first, we need to estimate the propensity scores. We have already introduced that. So that's a probability that an observation is going to be treated, right? And we can get the predicted probabilities. Okay, so what's going to happen in practice is that in some cases, for certain values of x, we can get a perfect prediction for probability of being treated, right? So what it means now is that from conceptual point of view, it violates the overlap assumption because we can say that those units have 100% chance of being treated, and that's against the overlap assumption. The second problem is that I've shown to you before is that if we have such case, then we are going to have 0 in the denominator, okay? And so that's a very unfavorable numerical artifact of that, right? So you see that overlap assumption is extremely important, and that's why we are going to deal with this tomorrow, right? So for estimation of treatment effect, the very obvious advice is drop observations where probability is close to 1. More specifically, we want this probability to be in the vicinity between 0.1 and 0.9. I can't stop to emphasize that, right? Obviously, it is going to the loss of data in both control and treated samples, subsamples. However, we need to maintain we need to maintain assumption, and we need to undertake this step in order to get consistent estimates. Okay, so once we get this, we can get the inverse probability weighting type of regression into steps. So we can estimate the propensity score as we have done in the previous state by running the logit model. And then recalling from the previous slide that the expectation of untreated state for treated subpopulation is given by equation 5.37, we can get a different estimate for average treatment effect. And now we are going to use the inverse probability weighting steps, right? So here, this small p is estimated consistently simply as a proportion of those in the this is not a control, sorry. So this is a treated samples. So this is the error. Sorry about this, right? So this is the another way of how we can get the estimate for average treatment effect using equation 5.38. So let us consider two estimators here, right? So one of them is given by estimating the equation 5.36 or 5.35. You see how different they are to equation 5.38, right? However, what we see is that these are two different approaches of estimating exactly the same thing, right? Because we remember that our main interest is estimate tau average treatment effect on the treated, okay? And make no mistake, this is still a difference in difference estimator, right? It's just it uses a different, more advanced ways of estimating the average treatment effect. Okay, so there are others. I'm considering only two here just to show you that this is what has been done in the modern difference in difference estimation, right? But there are more than that. Okay, now if you consider double robust estimators, right? So that's where different approaches are combined with one another, right? So for example, double robust estimator could be where the inverse probability weighting is combined with regression adjustment, right? And it has been shown that this, what is called inverse probability weighting regression adjustment, right, shows less bias than inverse probability weighting and regression adjustment separate. Okay, so the point is here is that econometrically there will be some improvements, right? And it's really important to keep track of them. But for me, in this training, it's really important to show you the differences and show that when you see some estimator in the literature, you will know what it actually means and how they were combined in order to obtain some estimator, right? And coming to the practical side of this, we are going to look at this tomorrow, but we are going to use the package DR DID to estimate that. DR stands for this DRE is doubly robust, right? So this is doubly robust difference in difference estimator, right? And here is a very simple sample. And you see here, you see IPW. So it means that this particular line tells you that this difference in difference has been estimated using inverse probability weighting, right? However, as we will see tomorrow, different options and different estimators are possible with this command. And so this is for you a practical implementation of the theories that we have just considered. Okay. The final thing I wanted to look at today is we've had this canonical treatment of the data that we have. However, as you may know, quite a lot of data that are available out there has more than 2 time periods. And obviously, we have already looked at one example where treatment happens in different time periods. So not only we have long panel data, but we also have treatments which are staggered, which happen in different time periods, right? So let's consider approach that can be implemented in this case, right? So the traditional DID, or I will call it also canonical DID, it entails data on 2 time periods and two groups, right? So we have data on individuals that are going to be treated, and there will be individuals who are never treated, and then we can apply either a fixed effect or get some other methods like inverse probability weighting or regression adjustment to get the treatment effect, right? But if you have heterogeneous treatment timing, two-way fixed effect that we considered before, in taking into account the individual effect and time effect, will be problematic because it will lead to biases of estimate and mislead averages for treatment average aggregated treatment effect. So the goal for us is to first of all estimate the group and time-specific average treatment effects. And here, this G is going to be an index indicating in which time period this group has been treated, and this is the time in which the observation is observed, right? So let us have a look at the canonical or traditional two-period DID setup, right? So we have the potential outcomes here, right? We have the observed outcome, which I have spelled out to you before today in the hour. And we can estimate the average treatment effect conceptually, but now I'm adding this panel data here in equation 6.40, right? So we need to make an assumption about the parallel trends, meaning that if the observation has not been treated, right, then it will follow the same trend as so the observations that have been treated, if they haven't been treated, they would follow the same trend that observations that have never been treated. So that's what parallel trend assumption is about. And if you do assume this parallel trend assumption, then the tau AT&T using the DID approach would be the difference between the post and pre in a treatment group. So this is what I call difference number 2, and this is difference number 1, the post and pre difference for the control group, right? So everything is beautiful so far, right? But when we estimate this using the two-way fixed effects model, it's not going to be robust to heterogeneous treatment effects, right? It works perfectly, as we have seen, if the treatment effects are homogeneous and if there are only 2 time periods. However, many times often, the treatment is staggered, right? It means that it has been introduced in different time periods in different individuals or more aggregated groups, and it is also heterogeneous. So the beta here that we can get in two-way treatment effect is going to be the weighted average for group G, and G is when the group gets treated, measured at time t, right? So this weight here is what we need to get the aggregation. Now the problem includes the possibility that the weights could be negative and they could be non-intuitive. They could be explosive in a sense, right? And so this beta coefficient that we are going to get in this regression does not recover the minimal average treatment effect, right? If treatment's actually different across groups or time when they are heterogeneous, right? And when they are staggered across different units, right? So the consequences of this, we cannot trust this beta coefficient because they are biased, and this beta could not be interpreted as causal averages because they also contain the treatment effect dynamics. Okay, so another treatment is required in this sense. And so we're going to make several assumptions here in order to make that estimation. And the first assumption we are going to make is that it's a staggered treatment, meaning that if particular observation has been treated in time period t, it remains to be treated in time period 1. Okay? So there is a very clear first period of treatment for each and every unit. And tomorrow I am going to show you the data set, how it looks. And so what it means is that it will permit construction for average treatment effect for a group after it has been treated, right? And it precludes treatment reversal or temporary exposure, right? So what it means, suppose that we have an observation in a group that has been exposed to a treatment in year 2. And then in year 5, the treatment has been reversed, so it stopped being treated. It's not possible to estimate the average treatment effect in this case. So what we assume is that once it is treated, so this is 0, this is 10. So once it is treated here in period 2, it is always treated, right? So we cannot say that it has been treated only like here and that's it. And here it's not treated again after 4, right? So this is a very important assumption that we are making here. And in your application that you're having, if you see the temporary exposure to a treatment, this is not a method that you can apply. The second assumption is the parallel trends assumption. And I'm splitting this into 2 parts. Assumption 2A, so that's using the never treated units. So what we are saying here is that the groups that were treated have the same trend as if they were not treated with the groups that were never treated. So this GI equals plus infinity means that they will be treated somewhere very far away in the future. So that's why we just call it then not treated in this particular sample, right? So why do we need this? Because it avoids contamination from treatment dynamics. We do not want to have the problems that two-way fixed effects model has, right? In plain language, what it means is that if the group that has actually been treated has not been treated, units would evolve, or the dynamic is going to be exactly the same as never treated units. Okay, so this is the first part of the parallel trend assumption, right? So a small note here about the condition on X. So conditioning is not strictly required here, but as in unconfoundedness in conditional mean, this is only going to be true in the randomized controlled trial experimental cases where the assignment to treatment is completely random, right? However, in our observational case, selection into treatment can be dependent on axis, right? And because we are doing the conditional difference in differences, so conditioning on X really matters, right? So all these assumptions that we have here with conditioning on X, they do matter for observational data. So the second part is of the parallel trends is not considering never treated, but not yet treated, right? So the intuition here is that the treated units would have evolved dynamically over time in the same way as those units who have not been yet treated by time period t. All right, so we have this parallel trend assumption that we have split into 2, right? And that's really important that they both hold. The third assumption is no anticipation and overlap. And we remember how important is that, right? Well, first of all, No anticipation is the very important assumption which I see being violated in quite a lot of applications, that units do not change their behavior before treatment actually begins. Why is it important? Because sometimes some units may anticipate that the treatment is going to happen, so they adjust their behavior, right? And obviously, if this happens, then the estimate is contaminated, and we don't have a pure treatment effect, right? We have an effect of anticipation, and we do not really want to include that, right? So, and overlap, we remember this is really important for estimation. So it's really important to keep that assumption in mind. So we have three assumptions here. Okay. And I see that we are approaching the end of this session. So I do not really want to run through this, and I do not have a lot to talk about, but still I have a couple of slides which are really important. So let me just keep this for tomorrow, and I will finish that in about 10-15 minutes. And right, I do not really want to rush through this because it's not going to be really useful for you if you do not actually see what we are doing in our empirical session. Good. Right. So thank you very much for your attention.